From Sojourner to Perseverance, a comprehensive analysis of 7 Mars rovers and their discoveries.
Introduction.
The exploration of Mars has evolved significantly over the past few decades with key contributions from a series of rovers. These robotic explorers have transformed our understanding of the Martian environment, geological history, and the possibilities of past life on the Red Planet. This report offers a comprehensive analysis of 7 iconic Mars rovers: Sojourner, Spirit, Opportunity, Curiosity, and Perseverance, highlighting their missions, discoveries, and the technological advancements that facilitated their success. 1. Historical context of Mars exploration. The journey began with Sojourner, which landed on Mars on July 4, 1997 as part of NASA's Mars Pathfinder mission. Sojourner was the first successful Mars rover, though it was small and limited in capability compared to its successors. Its primary objective was to analyze the Martian soil and rocks, providing the first close-up images and chemical analyses of the surface. Following Sojourner, NASA launched the Mars exploration rovers MER, Spirit, and Opportunity in 2003. Both rovers landed on Mars in January 2004 with a mission to search for signs of past water and assess Mars' potential to support life. 2. The Mars exploration rovers, Spirit and Opportunity. Spirit, operating from January 2004 until 2010, was tasked with investigating the Gusev crater, which scientists believed may have once been a lake. Over its 6-year mission, Spirit made significant discoveries, including detecting high concentrations of magnesium and iron carbonates at the Comanche outcrop, indicating a past environment that was wetter and warmer, potentially conducive to life. Finding silica-rich soil at home plate, suggesting the presence of ancient hot springs. Opportunity, landing shortly after Spirit, operated until mid-2018 and traveled over 28 miles 45 kilometers, setting a record for off-Earth rovers. Key findings from Opportunity include discovering blueberries, small hematite spherules that formed in the presence of water, which confirmed the existence of ancient watery environments. Identifying bright veins of gypsum near Endeavour crater, indicating that water flowed through the Martian crust. 3. Curiosity rover, advancing the quest for life. Launched in 2011 and landing in Gale crater in August 2012, Curiosity represented a leap in complexity and capability. Its mission focused on assessing whether Mars could have ever supported microbial life. Curiosity's key discoveries include evidence of ancient river systems and lake beds, suggesting that liquid water was present on the surface for extended periods. Analyzing the Martian atmosphere, including methane levels that could hint at biological activity. Curiosity's advanced scientific instruments, such as the ChemCam and SAM sample analysis at Mars, enabled detailed analyses of rock compositions and environmental conditions. 4. Perseverance, the latest frontier. Launched in July 2020, Perseverance landed in Jezero crater in February 2021. Its mission is to seek signs of ancient life and collect samples for future return to Earth. Perseverance is equipped with state-of-the-art technology, including a suite of scientific instruments designed to analyze Martian geology and climate, the ability to produce oxygen from the Martian atmosphere, a crucial step for future human exploration. Perseverance has already made significant discoveries, including identifying diverse rock types and analyzing regolith, which may provide clues about the planet's history and potential habitability. 5. Common objectives and key findings across missions. Across all missions, the primary goals have been to identify past water presence and analyze geological features, assess conditions that might have been favorable for life, understand the historical climate of Mars. The findings from these missions indicate that Mars once had conditions suitable for microbial life, with extensive evidence of water in various forms, such as ancient riverbeds and lake deposits identified by Curiosity. The detection of minerals like clay and carbonates that form in water revealed by Spirit and Opportunity. 6. technological innovations and instruments. The rovers employed advanced scientific instruments that enabled groundbreaking discoveries, including cameras, used for panoramic imaging and close-up analysis of rocks and soil. Spectrometers, analyzed the chemical composition of Martian materials. Rock abrasion tool RAT, exposed fresh rock surfaces for study. Each rover's suite of tools has been tailored to its mission objectives, allowing for a comprehensive understanding of the Martian environment. 7. Conclusion: the legacy of Mars rovers. From Sojourner's initial explorations to Perseverance's advanced studies, the legacy of Mars rovers illustrates a remarkable journey of discovery. Each rover has contributed uniquely to our growing knowledge of Mars, shaping future explorations and the quest for extraterrestrial life. The insights gained from these missions underscore the importance of technological innovation and persistent inquiry in understanding our neighboring planet. As we continue to explore Mars, the groundwork laid by these rovers will guide future missions and deepen our understanding of the possibilities of life beyond Earth. The discoveries made thus far not only enhance our knowledge of Mars but also inspire the next generation of scientists and explorers. The exploration of Mars through the missions of various rovers has unveiled numerous discoveries that not only enhance our understanding of the planet's geological and environmental history but also present counterintuitive findings that challenge our preconceptions about Mars and its potential for life. Counterintuitive discoveries. 1. Water in acidic conditions. While the search for signs of water has been a primary goal of Mars exploration, the findings indicate that ancient Martian water was often acidic, which may have posed a barrier to the development of life. For example, Opportunity's discovery of hematite blueberries suggested the presence of water. However, the acidic nature of that water could have made conditions less favorable for microbial life than previously assumed. This challenges the expectation that water alone is sufficient for life, as the chemistry of that water plays a critical role. 2. Warm, wet, and life-friendly environments. Spirit's findings at Comanche revealed rocks that were significantly richer in magnesium and iron carbonates than any other Martian rocks studied before. This suggests that Mars once had warm and wet conditions that were potentially favorable for life. The idea that Mars could have had a friendly environment in its past contrasts sharply with its current harsh and dry state, leading to the paradox of a planet that once may have supported life but now seems inhospitable. 3. Hot springs and life potential. The discovery of nearly pure silica at Spirit's home plate site indicated the past presence of hot springs on Earth. Hot springs are known to harbor diverse microbial life. This suggests that similar conditions on Mars could have supported life, challenging the notion that extremophiles are only found in particular environments. The implication is that life may have existed in various unexpected niches on Mars, not just in the traditionally habitable zones. For long-term viability of rovers, the longevity of the Spirit and Opportunity rovers defied expectations. Originally designed for missions lasting only 3 months, Opportunity operated for nearly 15 years. This unexpected durability raises questions about the robustness of engineering designs and the resilience of technology in harsh environments, suggesting that we may underestimate the potential for future missions to accomplish far more than initially planned. 5. Geological activity and life. The discovery of evidence suggesting explosive volcanic activity and steam eruptions at home plate poses a paradox. Volcanic activity, typically associated with inhospitable environments, could also provide the necessary conditions for life, such as the heating of water. This duality complicates our understanding of how life might have evolved under seemingly adverse conditions. 6. Clays as indicators of life. Opportunity's findings of clay minerals in neutral pH water suggest that some environments on Mars were indeed conducive to life. This finding contradicts the expectation that life might only thrive in more extreme conditions. The presence of clays indicates chemical processes that could support life, challenging the idea that only specific extreme environments are necessary for life to exist. 7. Environmental monitoring by Opportunity. Over its operational period, Opportunity collected extensive data on the Martian atmosphere, including dust storms and climate variations. This long-term study reveals that Mars is not a static environment and is subject to changes that could influence habitability. The ongoing monitoring of environmental conditions counteracts the assumption that Mars is a lifeless, unchanging desert. Conclusion: the discoveries made by Mars rovers, particularly Spirit, Opportunity, Curiosity, and Perseverance, highlight the complexity and dynamism of the Martian environment. Key findings challenge prevailing assumptions about the conditions necessary for life and the historical environmental conditions on Mars. As we continue to explore, the counterintuitive revelations from these missions will inform future exploration strategies and shape our understanding of what it means for a planet to be habitable. Through these rovers, we are not only uncovering the history of Mars but also redefining our concepts of life and survival in extraterrestrial contexts. The report on Mars rovers from Sojourner to Perseverance details the advancements in our understanding of the Red Planet through robotic exploration. While the overarching narrative emphasizes the discovery of water and the potential for life, several significant details and findings within the missions are often overlooked but hold crucial implications for planetary science and astrobiology. Key details likely overlooked. 1. Variability in past Martian environments. The report notes that Spirit discovered magnesium and iron carbonates at the Comanche outcrop, indicating a past environment that was not only warm but also potentially hospitable to life. Most summaries focus on the existence of water, but the specific chemical compositions provide insight into the variability of Martian climates. The presence of neutral pH conditions versus acidic conditions has profound implications for the types of microbial life that could have existed. Understanding the specifics of these environments helps scientists model ancient Martian climate dynamics and the planet's potential habitability. 2. The discovery of blueberries. Opportunity's discovery of hematite spherules termed blueberries is often highlighted as an iconic find. However, the fact that these formations are indicative of ancient watery environments is critical. What is frequently overlooked is the geological context in which these blueberries form. Their presence suggests specific sedimentary processes that occurred in liquid water, which are essential for reconstructing the planet's geological history and understanding the evolution of its surface. 3. Long-term monitoring of Mars. The report mentions that Opportunity monitored Mars's atmosphere and environmental conditions for over 14 years. Yet this aspect is rarely emphasized. This data is invaluable as it helps scientists understand seasonal and long-term changes on Mars, which can inform future missions and the search for life. The atmospheric opacity measurements, for example, are critical for understanding dust storms and their impact on solar energy availability for rovers in future habitats. 4. The technological innovations in rover design. Each rover utilized advanced scientific instruments, but the specifics regarding the rock abrasion tool RAT and its role in exposing fresh rock surfaces for analysis are often glossed over. The RAT allowed scientists to analyze previously obscured geological features and mineral compositions. This innovation not only improved the quality of data collected but also set a precedent for future robotic missions, highlighting the importance of tool development in planetary exploration. 5. Implications of volcanic activity. Spirit's findings at home plate regarding volcanic activity and the presence of silica-rich deposits suggest that Mars may have experienced hydrothermal conditions. This detail is crucial because it indicates that there were environments where life could thrive akin to Earth's hot springs. The potential for life in these hydrothermal systems is significant as they are often rich in nutrients and could support microbial ecosystems. 6. Geological history inferred from crater studies. Opportunity's extensive study of impact craters reveals not just their formation but also their erosion over time, which offers insights into Mars's geological history. While this is a fundamental aspect of planetary science, it is often overshadowed by the search for life. The erosion patterns in sediment deposits around craters can reveal past environmental conditions, climate changes, and the history of water activity on Mars. 7. Sample collection and future missions. Perseverance's focus on astrobiology and sample collection for future return missions is a major highlight, yet the implications of selecting specific geological samples are frequently underestimated. The choice of Jezero Crater, a former lakebed, for detailed study underscores the importance of targeting locations with the highest likelihood of preserving biosignatures. The strategic planning of sample return missions could fundamentally change our understanding of Mars's potential for past life. 8. Broader implications for astrobiology. The findings from all missions collectively support the hypothesis that Mars once had conditions suitable for life. However, the nuances of how these conditions varied are crucial for astrobiology. For instance, understanding the transitions from wet to dry conditions and how life could adapt or fail to adapt during these changes informs our search for life on exoplanets, enhancing our understanding of where and how life might exist beyond Earth. Significance of overlooked content. The significance of the overlooked details lies in their potential to reshape our understanding of Mars and inform future explorations. Each rover has built upon the findings of its predecessors, creating a comprehensive narrative of Mars's geological and environmental history. The subtle distinctions in the conditions that once existed on Mars not only enhance our understanding of our neighboring planet but also serve as a reminder of the complexity of planetary environments. Furthermore, the implications for astrobiology are profound. By studying the specific conditions under which water existed, the types of minerals formed, and the geological processes at play, we can better hypothesize about the potential for life. This knowledge feeds into the broader context of how we approach the search for life on other planets, refining our criteria for what constitutes a habitable environment. In summary, while the main narrative of Mars exploration focuses on water and the search for life, the intricacies of the findings, technological advancements, and their implications for planetary science are equally important. They provide a richer understanding of Mars's past and its potential for life, which is essential for guiding future missions and exploring the cosmos. 1. Historical contributions and discoveries. The Mars rover's Spirit and Opportunity, launched in 2003, transformed our understanding of Mars by identifying past water presence and potential habitability. Spirit's discovery of magnesium and iron carbonates indicated a warmer, wetter Martian climate, while Opportunity's blueberries provided concrete evidence of ancient watery environments. Curiosity and Perseverance built on these findings, with Curiosity revealing evidence of rivers and lakes and Perseverance focusing on astrobiology and sample collection in Jezero Crater. Known for its ancient lakes. Each rover's unique contributions have been pivotal in reconstructing Mars' environmental history and its capacity to support life. 2. Technological advancements and instruments. Each Mars rover utilized advanced scientific instruments, including high-resolution cameras, spectrometers, and specialized tools like the Rock Abrasion Tool (RAT). These instruments allowed for detailed geological analysis, mineral identification, and environmental monitoring. For example, Opportunity's PanCam captured panoramic images, while its alpha particle X-ray spectrometer APXS provided elemental compositions of Martian rocks. The technological evolution from Spirit and Opportunity to Curiosity and Perseverance showcases significant advancements in engineering and science, enabling more sophisticated exploration and data collection on Mars. 3. Common themes across missions. A recurring theme among all Mars rover missions is the quest for evidence of water and conditions that could support life. Each rover has contributed to understanding how Mars transitioned from a wet planet to its current arid state. The findings have consistently pointed towards Mars having once possessed conditions suitable for microbial life, highlighting the planet's dynamic history. This underlying objective unifies the missions as scientists aim to decipher the planet's past to inform future exploration and potential human habitation. 4. Impact on future Mars exploration. The legacy of the Mars rovers has set the stage for future missions, particularly with Perseverance's focus on astrobiology and the collection of samples for potential return to Earth. The data gathered by previous missions has informed the selection of landing sites' scientific objectives and the design of future rovers and instruments. The ongoing analysis of Mars' geology, climate, and potential biosignatures is crucial for understanding not only Mars but also the broader questions of habitability in the universe. The cumulative knowledge gained from these missions will guide humanity's efforts to explore and possibly inhabit other celestial bodies. 1. The Apollo Program 1961–1972. The Apollo program was a series of space missions undertaken by NASA with the goal of landing humans on the Moon and bringing them safely back to Earth. Notable missions include Apollo 11, which successfully landed astronauts Neil Armstrong and Buzz Aldrin on the lunar surface in 1969, marking the first time humans walked on another celestial body. The program provided extensive scientific data about the Moon's geology, surface composition, and potential resources, greatly enhancing our understanding of both the Moon and the broader context of solar system exploration. 2. The Voyager missions 1977–present. Launched in 1977, the Voyager 1 and Voyager 2 spacecraft were designed to explore the outer planets of our solar system. Voyager 1 conducted flybys of Jupiter and Saturn, while Voyager 2 flew by Jupiter, Saturn, Uranus, and Neptune, providing unprecedented images and data about these planets and their moons. The missions revealed complex atmospheric dynamics, ring systems, and magnetic fields, contributing to our understanding of planetary science and the conditions necessary for life. Both spacecraft continue to send data back as they venture into interstellar space. 3. The Hubble Space Telescope 1990–present. Launched in 1990, the Hubble Space Telescope has provided a wealth of astronomical data and stunning images of the universe. Its ability to observe distant galaxies, nebulae, and cosmic phenomena has led to breakthroughs in our understanding of the universe's age, expansion, and the existence of exoplanets. Hubble's observations have been instrumental in fields such as cosmology, astrophysics, and planetary science, influencing how we perceive the universe and our place within it. Its long-term operation has set a precedent for future space observatories and missions. Future outlook, predictions for Mars rover exploration. Introduction. The exploration of Mars has evolved remarkably since the first rovers landed on its surface, with spirit and opportunity marking the dawn of an era that has profoundly expanded our understanding of the red planet. As we analyze the trajectory of Mars rover missions, we can forecast several key developments and trends that are likely to shape the future of Martian exploration. 1. Enhanced rover technology. Future Mars rovers will likely incorporate even more advanced technologies than their predecessors. Innovations in artificial intelligence (AI) will enable these rovers to make autonomous decisions, allowing them to navigate complex terrains and conduct scientific experiments without direct human intervention. This will be critical for exploring regions that are too dangerous or inaccessible for human operators. Additionally, miniaturization of instruments will allow rovers to carry a broader array of scientific tools. This could include advanced spectrometers, more sensitive cameras, and specialized tools for in situ resource utilization (ISRU). Such advancements will enhance our ability to analyze Martian soil and rocks, increasing the chances of discovering signs of past or present life. 2. Collaboration with other missions. The future of Mars exploration will likely see increased collaboration between different space agencies and private companies. For instance, NASA's Artemis program and ongoing Martian missions could work together to gather more comprehensive data about Mars' atmosphere, geology, and potential for life. Shared data and resources will maximize scientific output and reduce operational costs. Moreover, the potential for joint missions involving orbiters, landers, and rovers could lead to a more integrated approach to understanding Mars. For example, orbiters could provide real-time data to rovers on the ground, helping them avoid hazards or identify scientifically interesting locations to investigate. 3. Human exploration and its impact. As robotic exploration continues, discussions about human missions to Mars are gaining momentum. The knowledge gained from rovers like Perseverance will be crucial for preparing for human exploration. Future missions may involve rovers designed to support human crews, providing essential data on the Martian environment, including radiation levels, weather patterns, and potential resources for life support. Human presence on Mars will also necessitate the development of new rover technologies. For example, rovers might be designed to transport astronauts between habitats and scientific sites, carry supplies, or even assist in construction activities. This integration of robotic and human exploration will pave the way for sustainable human settlement on Mars. 4. Focus on astrobiology. The search for evidence of life will remain a primary focus of future Mars rover missions. With Perseverance actively collecting samples for future return to Earth, the next generation of rovers will likely be tasked with following up on these findings. This could involve deploying advanced life detection technologies capable of analyzing samples for biosignatures such as organic compounds and microbial fossils. Furthermore, as we learn more about Mars' ancient environments, rovers may be sent to investigate specific sites of interest identified by previous missions. This targeted approach will increase the likelihood of answering fundamental questions about the planet's habitability. 5. Long-duration missions. Future rovers may be designed for long-duration missions, capable of operating for several years or even decades. Learning from the successes of Opportunity and Curiosity, which far exceeded their expected mission lifespans, future designs will likely incorporate more robust power systems such as nuclear batteries and self-repairing technologies. This will enable sustained scientific output and exploration in areas that require extended study. 6. Environmental monitoring. As we become more aware of Mars' changing environment, future rover missions will likely include a focus on long-term climate monitoring. Rovers equipped with advanced meteorological instruments could track changes in temperature, atmospheric pressure, and dust storms, providing valuable data for both robotic and human missions. This ongoing environmental monitoring will not only help scientists understand Mars' climate history but also inform future explorers about the challenges they may face on the planet. Such insights will be critical for ensuring the safety and success of human missions. Conclusion. The future of Mars rover exploration is poised for exciting advancements that will deepen our understanding of the Red Planet. Enhanced technologies, collaborative efforts, and a focus on astrobiology will drive these missions forward, laying the groundwork for eventual human exploration. As we continue to unlock the secrets of Mars, the legacy of rovers like Spirit, Opportunity, Curiosity, and Perseverance will undoubtedly inspire future generations to explore and perhaps even settle on our neighboring planet. The quest for knowledge about Mars is not just about understanding another world. It is about discovering our place in the cosmos.